Dear student, so today we are going to start module 1 of your analog and digital electronics. Module 1 covers field effect transistor such as FET and MOSFET and applications and operational amplifiers and applications of the operational amplifiers. So initially we will see field effect transistors. Now field effect transistors are three-terminal device. Field effect transistors are the three-terminal semiconductor device where the conduction is established by the carrier present in the device. So we know, all of you know, we have studied PN junction and bipolar junction transistor, BJT. Now first of all we have to see what is the difference between BJT and FET. So we will go through these notes. The major difference between BJT and FET is BJT is current control device whereas FET is voltage control device. That is the first point. I will explain you later this one. The second point is BJT is bipolar device and FET is unipolar device. The construction wise BJT is very difficult to construct or it involves which involves large process in fabrication, whereas FET is somewhat easier in fabrication. So BJT and FET, in this way it will differ. We will see some other difference later. Now FET is further classified as junction field effect transistor and metal oxide semiconductor FETs, MOSFET. In MOSFET, once again we have two classification, enhancement MOSFET and depletion MOSFET. So now I will take you to the slide. So the primary difference, I told you that BJT is a current control device. You see here, this is BJT. It is a current control device. That means output current IC is a function of IB. That means you change IB, the output current IC will vary. But our FET is a voltage control device. That is, output current ID is depend on whatever the control voltage apply between gate and source, that is VGS. So you change VGS, output current will be modified. So it is a current control device and FET is a voltage controller device. So now next, advantages of FET. I told you earlier, FET is a unipolar device, BJT is a bipolar device. Bipolar means voltage current is contributed in BJT both by means of positive charge and negative charge, that is nothing but holes and electrons. But it's in FET, it is either by holes or by electrons. That's why FET is called as unipolar device and BJT is called as bipolar device. Other than that, advantages of FET is it has got very high input impedance. If you have very high input impedance, it will not load the source. This is the one example, one advantage of FET. Whereas BJT has got lower input impedance, it will load the source. Second one is source and drain are interchangeable and low voltage, low current operation is possible, and FETs are less noisy. And no minority carrier storage. All these and very small in size, occupies very small space in IC. So all these are the other advantages of the FET over BJT. All these are the other advantages of the FET over BJT. Only the advantages of BJT is BJT will provide high gain, but FET will provide low gain, that is a low output gain. BJT will provide a high output gain. That is one advantages. Second one is BJT construction is robust, but FET constructions are very it can be damaged due to static charges easily. So that is the two advantages of the BJT over FET. So now you can see how the FETs are classified. FETs are classified as junction field effect transistor and MOSFET. We have seen earlier. In junction field effect transistors, we have two types. One is N channel and other one is a P channel JFET. In MOSFET, we have two types. One is enhancement, other one is a depletion. Enhancement, we have N channel MOSFET, E MOSFET and P channel E MOSFET. Once again, in depletion, we have N channel D MOSFET and P channel D MOSFET. All these things and the behavior of all these things, characteristics of all these things we are going to study. So now first, what is JFET? JFET is called the junction field effect transistor. So it is a three-terminal device where output current is controlled by voltage across the input. So JFET JFETs there are two types. One is called a P type, other one is called as a N type. One is called as P type, other one is called as N type. Now we will see the construction of JFET. So this is the construction view of JFET. You can see here. So it contains, there are two types, N channel JFET and P channel JFET. In N channel JFET, very huge or large amount of semiconductor material of N type. On the one end of that is connected to the terminal through ohmic contact, and other end of that is connected to the terminal through ohmic contact, and that is called as source, and one terminal is called as drain. And on this N channel material, we will dop P channel material, P type of semiconductor material to form the junction. You can see here there are two P types of semiconductor material which is in turn connected and form the junction. That's why the name it is junction field effect transistor, and this junction we will refer as a gate. So FET is a three-terminal device. One is a drain, second one is source, and third one is a gate. This is the N channel. And in P channel FET, we are using a semiconductor material of PG, which acts like a channel for the flow of current, and over which N type of dopant is added to form the junction. So this is the feed channel. Once again, three-terminal semiconductor device, three-terminal device. One is drain, second one is source, and third one is the gate. So this is the architecture view of our junction field effect transistor. So now next we will move to how it is constructed. We will see just through the animation. You can see here N type of semiconductor material over which we will add, that is called as, the process is called as a dopant, P type of semiconductor material, and in between CP type of semiconductor material there is a small region that is called as a depletion layer, and this P type of semiconductor material in turn it is internally connected, and that is referred as gate, and other end of this N type of semiconductor material is connected to terminal through ohmic contact, and it is called a drain. Other end of the N channel semiconductor type material is connected to the terminal through ohmic contact, it is called a source. So this is the channel here where the electron flows, and this is the symbol for N channel JFET and P channel JFET. So here you can see in the N channel the arrow is heading towards the gate. The arrow is heading towards the gate, and in the P channel the arrow is moving away from the arrow, is moving outside from the gate. So this is the way we will differentiate between N channel and P channel, and ID is the drain current. This is the gate is positive here, and this is the positive terminal, and this is the negative terminal. This is the VDS, potential between drain and source, and this is the potential between gate and source. So this is the N channel, symbol for N channel MOSFET, and this is the symbol for P channel MOSFET. Now how this works? So we have to see how this works. So before that we have to see what do you mean by depletion layer, and what is the function of a depletion layer, how it works. For that I will use whiteboard. So depletion layer. So we have studied we have studied p type of we have studied p type of p-n junction. P-n junction is nothing but something like this. We will represent p-n junction something like this. This is the positive terminal and this is the negative terminal. So what it contains? It contains p type of material, and n type of material, n type of semiconductor material. So here in this p type of semiconductor material, majority carriers are holes and minority carriers are electrons. Here n type of material, majority carriers are electrons and minority carriers are holes. So these two junctions are separated by some type of region. It is called as depletion region, because whenever some of the charges, positive charges, moves from here to here, it will leave negative ion. And whenever negative electrons moves from here, negative charges or electrons moves from here to here, it will leave positive ion. So this region is depleted by means of charges, depleted by means of any charges. That's why it is called as a depletion region. It is called as a depletion region. Now we will bias this semiconductor material. When you bias this semiconductor material, there are two types of bias. One is called as forward bias, other one is called as reverse bias. Suppose if I connect P end of this one to the P terminal of the source, and negative N end of this one is to the negative terminal of the battery source, then it is called as a forward bias. Because forward bias will decrease the depletion region, or decrease the size of the depletion region. Now, what do you mean by reverse bias? We will see what do you mean by reverse bias. So if I connect P end of this material, P end of the semiconductor material to the negative terminal of the battery, and if I connect positive terminal of the battery to the N type of material, then it is called as reverse bias. What will happen when in the case of the reverse bias? In the case of the reverse bias, this holes here will get attracted towards this negative end, and these electrons here get attracted towards the positive end. That means the depletion region size will get increased. So during the reverse bias, depletion region size will get increased. What will happen if I keep on increasing the reverse bias? I will reach the stage. That stage is called as avalanche breakdown. What do you call that stage? Is called as avalanche breakdown. What is the meaning of this one? Avalanche breakdown is the one where there won't be any more p-n junction, and this entire p-n junction acts like a semiconductor material, and the current will shoot up and that will destroy this p-n junction, and that is called as avalanche breakdown. So this concept is required. So when you increase the reverse bias, it will reach something called as avalanche breakdown. With this information, now we will move to once again to our slide. So now you can see here operation of the field effect transistors. Here you can see P type is connected to gate. This P type is referred as here. P type is here. It is referred as a gate and source and drain. And this is the depletion region. It has got constant width right now. Now, when you increase the reverse bias, here in the diagram you can see we have connected initially VGS to 0. VGS to 0 means gate and source I have shorted, and there is no potential is given between gate and source. Now source is at the gate and source is at the lower potential, and here between drain and source we have connected the source like this. That means this is N type of material. N type of material is connected to the positive end. N type of material is connected to the positive end of the battery, and this one is positive gate is positive material. P type of material is connected to the negative end of the battery. Then it acts like reverse bias. So now we have to see, by varying this reverse bias voltage, how the current will be modified, and that is known as output characteristics. First we have to see output characteristics. Then after that, by varying VGS, how the current will be modified, ID will be modified. That is called as transfer characteristics. That one we have to see. That is called as transfer characteristics. So we will see first, initially VGS is 0, and we made VGS is 0, and we will see how this works. You can see here, when you increase the potential difference, that is VDS reverse bias, then all the electrons here, it will get attracted towards this positive end. So electrons will get attracted towards the positive end. So when the electron moves from here to here, that is like this. Conventional current according to physics moves from like this. That is ID moves like this. So when electrons moves like this, ID moves like this. Then what will happen if you keep on increasing this one? When you keep on increasing this one, then this end will be at more reverse bias than this end. So here you can see depletion. When we increase the reverse bias, the depth of the depletion region will increase. You can see here, this is the depth of the reverse bias, depletion region will increase, and at the one point, both this end here will touch, and that point is called as pinch off voltage. So pinch off voltage is the condition where both end of the depletion region will touch and the movement of the current will be restricted. Actually, according to that pinch off voltage, pinch off condition, current should be 0, but here current will be saturated and current will be maintained at the particular saturation rate. So we will see now this one. So initially, when you increase VDS, current will increase. You can see current will increase in this rate. Till what? Till it reaches pinch off voltage. When at the pinch off voltage, our current is called as IDSS, drain source. IDSS, saturation current. At this point, further increase in the voltage. At this point, further increase in the VDS will not increase in the current. Current will remain saturated. So this one is called as pinch off voltage, and this condition is called as pinch off condition, and this region is called as ohmic region. Ohmic region means which will follow the Ohm's law, V is equal to IR, and this one is called as our saturation region. Saturation region, irrespective of increase in the drain to source voltage, current remains same. This is called as saturation region. So now if you keep on increasing VDS, at somewhere it reaches avalanche, it will reach avalanche breakdown, and our current will shoot up and it will destroy the semiconductor material. It will destroy the PN junction. So this is the operation of junction field effect transistor. So you in the diagram you can see, as you increase VDS, both will touch, both the depletion region at the drain will touch. You may ask why it is not touching here, because VDS, it is this end is more reverse bias than this end. This end is normally at 0 potential, but this end is at larger reverse bias. So our depletion region size will increase, and this will block the flow of electrons. This will block the flow of electrons, and current will get reduced. Current will get reduced, and current will be saturated. This you can see, and this condition is called as a pinch off. This condition is called as a pinch off. So now we saw the operation of this one. We saw the operation of this one. VGS is equal to at 0. Now if we reduce the VGS, less than 0 volt. So if we reduce the VGS less than 0 volt, here you can see VGS is connected in the reverse bias, and I am giving negative voltage here. If I am reduce it, if I am increase this one VGS, if I am reduce the VGS less than 0 volt, then current will be further decreased. Pinch off occurs, pinch off stage occurs at earlier. You can see in this diagram here, when VGS is 0, you can see pinch off occurs here. When VGS is 0, you can see pinch off occurs here. But when you increase the VGS in the reverse way, or if you give VGS in the negative voltage, pinch off occurs somewhere here. If the VGS is equal to minus 2 volt, pinch off occurs somewhere here. If the VGS is equal to minus 4 volt, pinch off occurs here. So like this you can control the current by controlling the voltage. Hello student, welcome back. The next topic is biasing MOSFET. So here we will study biasing depletion MOSFET and biasing enhancement MOSFET. That means we will study the techniques for biasing depletion MOSFET and the techniques for biasing enhancement MOSFET. So in depletion MOSFET, first we have to study what do you mean by first we have to study what is biasing. What is biasing? So before explaining biasing, let us take our MOSFET. So this is the MOSFET, and using MOSFET we have designed something called as an amplifier. Using MOSFET we have designed something called as amplifier. So this is nothing but an amplifier. Now if I ask you question, what is amplifier, you will tell it will amplify the signal, but that would look like a silly answer. An amplifier is a device which amplifies a small signal. For example, for this input to this amplifier is, I will give the input to this amplifier. This is a small signal of 1 kilohertz, and the amplitude of this one is around 10 millivolt. So this signal is applied to the amplifier. The output of the amplifier is something like 20 millivolt. Output of the amplifier is 20 millivolt. But the time period is remain same. The time period here, it is, suppose here the time period is something T1. Here also the time period is T1. So here also the time period is remain same. Only the amplitude of the signal will get amplified. Only this one will get amplified. So now this amplifier amplifies this signal with the factor of 2. Suppose if I give different signal, like with the different frequency, if I give different signal with a different frequency, or if I give some different signal, this amplifier has to amplify this with the amplification factor of 2, irrespective of different parameters. That means, in order to amplify with irrespective of different parameters, with the factor of 2, I need to give some voltage, and that voltage is called as DC voltage. I need to give some DC voltage or DC bias. That is called as DC bias. For example, we know our characteristics curve, output characteristics curve for our this MOSFET is something like this. That is, this region is called as ohmic region, and this region is called as saturation region. This is called as a saturation region. So by giving this value VDS, I can make this my MOSFET either work in the saturation region or in the ohmic region. So that value is called as biasing. That value is called as biasing, and that process is called as biasing. The minimum amount of voltage that will take you JFET or MOSFET in this either in the linear ohmic region or in the saturation region is called as biasing. So with this, this one, we will proceed to the different types of biasing in the enhancement MOSFET and in depletion MOSFET. There are different techniques. Total techniques are something like this. One is called as cell bias. Other one is called as voltage divider biasing. Third is called as feedback bias. So all these are different types of configuration we are used in biasing. So my dear students, so first one you will take biasing depletion MOSFET. For depletion MOSFET, there are two types of biasing method. For depletion MOSFET, there are two types of biasing. This is the first one, self bias. Second one is called as voltage divider bias. First one is the self bias. Second one is the voltage divider bias. In your notes, please make a note. This one, this is the second one, this is the first one. First you will see here self bias. First we will see here self bias. What is self bias? What is cell bias? We will take the circuit diagram. What is cell bias? So now here this is a depletion MOSFET. What type of MOSFET it is? It is N channel or P channel? Yes, N channel or P channel? This is N channel, because by seeing this you can say the arrow is towards inside, right? That's why this is N channel. And we have gate terminal, we have drain, and we have source, and the fourth terminal is shorted with the source, and drain resistance RD is 0.4 kilo ohm, and this is our VDD. This is our VDD. So this is our VDD. So this is our VDD. This is our VDD. VDD, voltage between a drain. This is our VDD, and this potential is known as VDS, voltage between drain to source, and this is VGS. So now with the example we have to try to understand this concept. What is cell bias? Cell bias means it will automatically generate whatever the voltage required to move from one region to the other region, that is linear region to ohmic region to saturation region. This is automatically generated. That is called as a cell bias. So we will see, my dear friends, how this works. So we will move to the configuration. We will see how this works. So now, given saturation drain current, we will solve the problem. Saturation drain current is 8 milliamps, and pinch off voltage is -2 volt. Determine the value of the gate source voltage. So you have to determine here, the value of gate source voltage. That is VGS you have to determine, and you have to determine the drain current and drain source voltage. You have to determine drain current ID, and you have to find out VDS. You have to find out VDS. You have to find out VDS. So here first we will take What is VGS? VGS is already given here. 2 volt. And pinch off voltage is minus 2 volt. Pinch off voltage. See, given, so which type of this one? This is a depletion. Depletion MOSFET, right? So gate source voltage is 2 volt. Gate source voltage is 2 volt. Sorry, gate source voltage here, it is represented 2 volt. Then polarity of the voltage, it says here, polarity of the voltage be applied between the gate and source terminal in such a way that the MOSFET operates in the enhancement region. The MOSFET operates in the enhancement region. How will come to know the MOSFET operates in the enhancement region? How will come to know the MOSFET operates in the enhancement region? So, how will you come to know the MOSFET operates in the enhancement region? So here you can see depletion MOSFET, we know depletion MOSFET works in either depletion region or in the enhancement region. But when the gate to source voltage is positive, then it is in the enhancement region. So we have here 2GS, we have here 2GS, we have here VGS is equal to 2GS. That means it works in the enhancement region. So it works in enhancement region. So now for depletion MOSFET, the formula is, we have the formula for depletion MOSFET, we have the formula for depletion MOSFET. This is the formula for depletion MOSFET, right? To find IDSS 1 minus VGS VP square. So we know IDSS, drain saturation current is, we know VGS 2 volt, we know VP 2 volt. So when you substitute this one, you can find out ID is equal to 8 into 10 to the power 3, 1 minus 2, 2. Minus and minus becomes plus. So when you solve this one, you will get 32 milliamps. You will get 32 milliamps. That we got ID. Now next one is applying the Kirchhoff voltage laws to the output section. You have to apply the Kirchhoff voltage laws to the output section, and you have to find out the VDS. So how to apply the Kirchhoff voltage law to the output section? This is our output section. See, this is our output section. Here you have to apply the Kirchhoff voltage law. What is Kirchhoff voltage law says? Kirchhoff voltage law says algebraic sum of the voltage source and voltage drop across various resistors is 0. That means here it is VDD. That is we have connected something like this VDD. We have shown this is in the single-handed notation, but it is connected something like this. This is 18 volt. That means you have to apply Kirchhoff voltage laws. That is 18 volt. 18 minus here it is current is ID and RD, and this is ID and this is RD minus VDS is equal to 0. This is the Kirchhoff voltage law. The algebraic sum of the voltage source and the potential, this is voltage drop across various resistors, is equal to 0. So 18 we got it. 18 is nothing but our VDD. Here we have single-handed notation. This is single-handed notation. Single-handed notation means you just show like plus 18 volt. But how we will connect in the real scenario? We will connect something like this, plus and minus. So 18 minus ID RD. That is the here current is ID. And now when this current flows through this resistor, then the drop IDRD minus drop across drain to source VDS is equal to 0. This one this is called as Kirchhoff output law. Now applying that law, you can see here 18 minus ID ID is nothing but this one, and our RD is nothing but this one, minus VDS is equal to 0. Here in this equation, I know, see, we know this one, but we don't know VDS. We don't know one quantity, and it is equal to 0. That means you can solve this one, and you will get VDS is equal to 5.2 volt. So now this VDS is called as Q point or bias point. VDS is equal to 5.2 and VDS is equal to 5.2 and IDSQ. VDSQ quotient current and IDSQ quotient current is equal to 5.2 and 32. This is called as our bias point. That means giving this voltage, we can put this into saturation region. So this is called as biasing.